carbonate-containing species is certainly bicarb iron. No carbonate to speak of, because we've got a pH that's less than 8.00. We've already recognized that a pH of 8.00, the bicarb molarity is greater than the carbonate molarity by a factor of 210 to 1. So when we're looking at a pH on the order of 7, the bicarb molarity is much greater than the carbonate molarity, now by a factor that's at least 1,000 to 1. More than that. 2100 to 1 if we took the pH to be 7.0. pH is above 7.0. Nevertheless, still the system is acidic. Nevertheless, the system is more acidic than pH 8.00. And we said that this reaction will also be the principal source of ammonia. But in order to, in a detailed and more precise fashion, consider the molarities of the various species in the system, we have to ask the question, is there any source of calcium ion in the system beside the reaction of calcium carbonate with ammonium ion? Yes, there is. I wrote that right here. Because calcium carbonate is surely capable of still reacting with water in the system. It shall not be expected to react with water nearly as effectively as it reacts with ammonium ion, because ammonium ion is a much stronger acid. Now, we've already looked at the reaction of calcium carbonate with water. K value is here, compared to the K value of calcium carbonate reacting with ammonium ion. Neither of these values are big, which we recognized last time. They're in fact both very small, but this value is not nearly as small as this value, which is telling us this system is certainly a better source of calcium ion than this system. Same for ammonia. Is there any other possible source of ammonia in the system beside the reaction of calcium carbonate with ammonium ion? The answer is yes. If the gang-up factor goes to a measurable extent, ammonium ion in excess relative to the amount of carbonate ion total that's in the system, there can be some conversion of bicarb to H2CO3, which also produces ammonia, and ammonium ion plus water, which of course is nothing but Ka for ammonium ion. So when we look at the information we've so far considered, we can answer the question, how must the calcium ion molarity and the ammonia molarity compare in the system? Calcium ion molarity and ammonium ion molarity. Pardon me, calcium ion molarity and ammonia molarity. We've got that written here, right here. How can we conclude that the ammonia molarity in this system cannot be lower than the calcium ion molarity, and in fact might be somewhat higher? How can we make that conclusion legitimately so? The ammonia molarity cannot, in this system, be lower than the calcium ion molarity. In fact, the ammonia molarity might be somewhat greater. Why is that a fair statement?
With the K values for your third reaction?
Well, let's look at the K values. This reaction produces ammonia and calcium ion. This reaction produces calcium ion but not ammonia. This reaction has a K value of 1.3 times 10 to minus 12. This reaction can be expectedly negligible even though it's got a substantially greater K value, because the total carbonate in the system isn't going to be very much. Why is that a fair statement? Well, we already looked at this K value for this reaction, and this K value is telling us the solubility of calcium carbonate in this system, whatever it is not very great at all. But how about this reaction? ammonium ion plus water, because clearly these are abundant species in the system, which is Ka for ammonium ion, 5.6 times 10 to minus 10. How does 5.6 times 10 to minus 10 compare to 1.3 times 10 to minus 12? Recognizing that when we look at this K value, we're talking about a reaction which makes calcium ion but not ammonia. And we talk about this K value, Ka ammonium ion, we're talking about a reaction that makes ammonia but not calcium ion. This K value is bigger than this K value. So, does it seem fair to say, based on looking at the K information we've got tabulated on the board, that the ammonia molarity in this system cannot be lower than the calcium ion molarity, and in fact might well be a little bit higher? Are we seeing this? I hope. Again, we looked at the two reactions which make calcium ion and all the possible reactions which can make ammonia. And even if we neglect this reaction, Ka ammonium ion, which is an ammonia-producing reaction, and it involves principal species certainly in the system, is a bigger number than K for this reaction. So this reaction makes ammonia more effectively than this reaction makes calcium ion. Well, that tells us the ammonia molarity in this system cannot be lower than the calcium ion molarity and might in fact be a little bit larger. Now what about the bicarb molarity? Is there any reaction in the system which is going to have an impact on bicarb bicarb concentration, beside this reaction? Well, we looked at this reaction. That'll contribute somewhat, but not much to the bicarb ion. And what about this reaction? This reaction which can go based on the gang-up factor. Remember again, the gang-up factor is a consequence for this system of the ammonium ion molarity being a whole lot greater than any carbonate that's in the system. Because we've already assessed the calcium carbonate solubility to be 4.2 times 10 to minus 3, and that's a hell of a lot smaller than 1.0 molar. The impact of this reaction on bicarb molarity is what? What is the impact of this reaction on bicarb molarity? Doesn't this reaction consume bicarb? Well, then the impact of this reaction is to make the bicarb molarity come down. Right? This reaction will make the bicarb molarity come down while it makes the ammonia molarity go up. So, the assessments we've now made tell us that the ammonia molarity and the bicarb molarity must compare how? The ammonia molarity and the bicarb molarity. How must those molarities compare? Ammonia molarity, if anything, should be a little bit larger than the bicarb molarity. All we're doing is letting the chemistry of the system talk to us. Now I know it's complex because there's a lot of equilibria that we have to look at. But we've looked now at all the tools that are necessary to get at solution properties like hydronium ion concentration. This we did in chapter 18. So we're taking those tools and applying those tools to this system, which clearly depends on acid-base chemistry, the dissolving of calcium carbonate in the presence of ammonium ion. And what are the other reactions, other equations that are pertinent to this system? Material balance. Sum of ammonium ion and ammonium molarity is 1.0 because we had 1.0 molar ammonium chloride solution. And the solubility of calcium ion, which is equal to the sum of the concentration terms for all the possible forms of carbonate ion. And the remaining equation is charge balance. Here's the complete charge balance equation. Now what should we do with this charge balance equation when we write it? Because at this point, we've looked at all the pertinent equilibria. We've got all the equations written that we need to pay attention to. So when we get to this charge-balance relationship, does it seem reasonable to you that we want to simplify it to the extent that we can? So we've written here, hydroxide molarity is Kw over hydronium ion molarity, so this is not an unknown. The chloride ion molarity is known, because it's 1.0 molar ammonium chloride solution, and the chloride ion doesn't react with anything in the system, so that's a fixed number of 1.0. And the carbonate molarity can always be expressed in terms of the calcium ion molarity by way of KSP. So we really don't have that many unknowns. Now, the complete detailed solution for this problem is available to you. I put it to the class last summer on bonus quiz number 2. If you take the relationships which we have over there and solve for calcium ion, you'll find that you can solve for calcium ion in terms of hydronium ion as the only other so-called unknown. It winds up looking like this, which may at first look clumsy, but this is not a difficult relationship whatsoever. And if we now wish to proceed with solving for the calcium ion molarity rigorously, because we've got all the equations and equilibrium reactions assembled that are germane to the system. We've got what we have. The detailed solution can now be proceeded with. And what we're trying to do is to find out how this solution keeps with our experimentally observed value for the hydronium ion concentration, which by this relationship gives us the calcium ion concentration, which is the solubility of calcium carbonate. Now, the final steady reading we have for pH for this system is 7.23. So I will offer the arithmetic part of the puzzle to you for practice. I guarantee that any questions I might ask for this system or any similar systems on any quiz or exam would not involve doing the arithmetic, because that's too time-consuming. But we've shown you here the kinds of things that you need to demonstrate knowledge of, because these are the considerations which are the chemistry of the system, and that's what we want. So, have a go at it if you wish. The complete solution is available to you on bonus quiz number 2 from summer 11 if you've not yet looked at it. So we'll move forward in chapter 19 and pick up from our point of departure where we were looking at the calcium hydroxide equilibrium with calcium ion and hydroxide ion. And said, what happens to that equilibrium system if you subject it to various treatments? The treatments included treatment with more water, treatment with calcium ion, treatment with hydroxide ion, treatment with hydronium ion, treatment with ammonium ion, treatment with ammonium ion and sulfate ion. And after all of those treatments, we assessed the result of the treatment in completing the table that you see in the notes on page 1960. Following that, on page 1917, let's think in brief about converting calcium carbonate into calcium sulfate, gypsum. Recall, if you will, when we talked about treating calcium hydroxide with ammonium ion, we found out that the calcium hydroxide was dissolved readily by ammonium ion. The K calculation for that reaction told us that. The K calculation for treatment of calcium hydroxide by ammonium ion was on the order of 10 to the 5th. It was 9.3 times 10 to the 4th. Now we looked at treating calcium carbonate with ammonium ion. And even though carbonate ammonium ion is a large extent Bronsted-Lowry acid-base reaction, for this equilibrium system we get a K value of 7.2 times 10 to the minus 8. So we're seeing to dissolve calcium hydroxide by treatment with ammonium ion, that works like goes like a shot. But to dissolve calcium carbonate by treatment with ammonium ion, that's not getting you any place at all. Why do you think calcium carbonate might be so much more stable in the presence of ammonium ion compared to calcium hydroxide? Even though ammonium ion plus carbonate ion is a large extent Bronsted-Lowry acid-base reaction. Any ideas why the calcium carbonate resists quite effectively attack by ammonium ion, whereas calcium hydroxide is readily destroyed by attack by ammonium ion? Any ideas about the great difference between the thermodynamic impact on the stability of calcium hydroxide versus the stability of calcium carbonate by treatment with ammonium ion? Any ideas? Well, what about the extent of the acid-base reaction? We know ammonium ion reacts with carbonate ion to a large extent. How about ammonium ion and hydroxide ion? Is that even a good deal larger extent? Yeah, because hydroxide ion is a lot stronger base than carbonate ion. What about lattice strength? Just for curiosity's sake, in Chemistry 2045, you talked about solid state structure, I'm sure, but I don't know to what extent you talked about solid state structure. In Chemistry 2045, when you talked about solid state structure, and you did things like examine the lattice for simple cubic and body-centered cubic and face-centered cubic materials for elements, you did that, right? Okay. What about the ionic lattice? Did you do anything with the ionic lattice in Chemistry 2045? I'm curious. Yes or no? Ionic lattice. Didn't do anything with the ionic lattice. You recognize that the ionic lattice is a much more complicated problem compared to the lattice of a metal? Why is that true? Why is the ionic lattice a much more challenging problem, a much more difficult to understand lattice compared to the lattice of a metal? Why is that? You know me, I keep poking around to find out what you did in 2045. See if you learned the stuff I hope you learned. Why is the metal lattice a much simpler problem, a much simpler lattice? Well, in the metal lattice, like the iron lattice, does it make any difference which iron atoms are next to each other? Well, they're all iron atoms. Who cares what iron atoms are in contact with other iron atoms? They're all the same. But how about in the sodium chloride lattice? Is the sodium chloride lattice made stable by sodium ions touching sodium ions? Chloride ions touching chloride ions? No. So you've got an arrangement problem which you don't have with the metal lattice. For an ionic lattice to be stable, you need maximum contact between ions of opposite charge and minimum contact between ions of like charge. Did you ever recognize that ionic lattices are all quite brittle, but metal lattices, they're stable. Even if you bend them and twist them, metal lattice is still stable. You ever had a crystal of rock salt? You try to reshape it by bending. What happens to the crystal? Snaps, it fractures. Why is that? Well, and back into the metal lattice, it doesn't make any difference which iron atoms are in touch with other iron atoms. But in the ionic lattice, if you have a nice big crystal of rock salt, sodium ions and chloride ions, and you try to reshape that crystal by bending, you wind up forcing contact between ions of like charge and reducing contact between ions of opposite charge. Well, as soon as the like charge contact exceeds the opposite charge contact, bam, the lattice explodes. Coulomb's law. So the ionic lattice is a more challenging problem because you have a much more rigorous arrangement consideration with which to wrestle. And you've got to have oppositely charged ions in maximum contact with each other and minimum contact of like charged ions. Because the more contact you got of like charged ions, the weaker, the less stable the lattice. In any case, the two lattices we're asking about are these two. We found out this one is readily destroyed by ammonium ion attack, so it must be a much weaker lattice. This one is not readily attacked at all by ammonium ion. Not effectively, pardon me. Do you think there might be an even more challenging arrangement problem in making a calcium hydroxide lattice compared to making a calcium carbonate lattice? You see, for calcium hydroxide, the formula for the salt tells you for every calcium ion you got in this lattice, you got 2 hydroxide ions. But for calcium carbonate, for every calcium ion you got 1 carbonate ion. So arranging the ion components of calcium hydroxide is even more difficult than arranging the ion components of calcium carbonate with respect to each other. Because in calcium carbonate, you got a 1-to-1 ion ratio. Now, what do you think about the average attraction between and among calcium ions and hydroxide ions in this lattice compared to calcium ions and carbonate ions in this lattice? Where do you think the attractions might be stronger? Calcium carbonate, why?
Greater charge.
Well, carbonate's -2 like calcium ion. But hydroxide ion is only -1. Well, Coulomb's law tells us that force of interaction between charged particles is directly proportional to charge magnitude. 2 plus to 1 minus for calcium hydroxide. 2 plus to 2 minus for calcium carbonate. These are some of the reasons why calcium carbonate lattice is a lot more stable. Which again, the result that we've observed on treatment with ammonium ion we've already become aware of. Now back to calcium carbonate. And now talking about turning calcium carbonate into gypsum. If I put you in the laboratory and I ask you to make this conversion, tell me, how many of you in 46 laboratory are now through with assignment 3? Okay. Well, then you've already done this. So you should know about this. Your job is to turn calcium carbonate into this stuff. you find on the side shelf available for this conversion. Sodium sulfate solution, ammonium sulfate solution, sodium hydrogen sulfate solution, and sulfuric acid. Clearly, you must have a system which makes available sulfate ion. Each of these systems makes available sulfate ion. What is your choice? I got to vote for sulfuric acid.
How would the strong acid compare to the double attack of the ammonium?
Well, you argue this to be a double attack on calcium carbonate.
Sure.
Which it is. Is this a double attack on calcium carbonate?
No. Yes.
Is this a double attack on calcium carbonate? No yes or just yes?
Yes.
Yes, good. For this system, tell me the double attack on calcium carbonate. Hydrogen sulfate ion to
Carbonate.
to murder carbonate, and hydrogen sulfate ion to you got to do two things here. I mean, pardon me, you don't have to do two things here. But before we go further with that, let's look at this. How many attacks do we have when we treat calcium carbonate with this? Just one. Sulfate ion to go after calcium ion. Here, you got two attacks. Ammonium ion to go after carbonate ion, and sulfate ion to go after calcium ion. Here, two attacks. Hydrogen sulfate ion to go after carbonate ion, and hydrogen sulfate ion to make available sulfate ion. Which one attacks carbonate ion far more effectively? Ammonium ion or hydrogen sulfate ion? Why? Bigger Ka value, but tell me by experiment, how would you know if we put some calcium carbonate in a beaker and treat it with ammonium ion, and next to it we put some calcium carbonate in a beaker and treat it with hydrogen sulfate ion? How would you know the hydrogen sulfate ion attack is far more effective?
More gypsum will form.
Less calcium carbonate.
Well, I agree with that, but I want to know if you would see anything dramatic which would be screaming at you that the hydrogen sulfate ion attack is far more effective than the ammonium ion attack. Didn't we just attack some carbonate ion with ammonium ion? We did that here, didn't we? You see any bubbles? You think if we hit calcium carbonate with hydrogen sulfate ion, we'd see bubbles? Look at the acid-base table. Back to that. We haven't looked at that for a couple days. Time to look at it again. One beaker, you treat calcium carbonate with ammonium ion. Second beaker, you treat calcium carbonate with hydrogen sulfate ion. What observation would you make to tell you that the hydrogen sulfate ion attack is far more dramatic? Bubbles all over the place. Because to get bubbles, you've got to turn carbonate ion into this stuff, given that this stuff readily decomposes into water and CO2. Can I readily turn carbonate ion into this stuff by treating with ammonium ion? The answer is no, because ammonium ion is a much weaker acid than this stuff. But if I treat carbonate ion with hydrogen sulfate ion, then I see bubbles all over the place, because hydrogen sulfate ion is a lot stronger acid than this stuff. So notice, if you hit ammonium ion with carbonate ion, pardon me, if you had carbonate ion with ammonium ion. You can turn carbonate into bicarb ion, there's no question about it. But you're not really removing the carbonate from the system. But if I take carbonate and beat up on it with hydrogen sulfate ion, I'm really going to take the carbonate out of the system, because I'm going to effectively convert the carbonate to this stuff, and this stuff's going to leave the system. CO2 gas bubbles all over the place. Well then, if my recollection is correct, the first choice that I heard from you folks from this list of possibilities, A, B, C, D, was to hit the calcium carbonate with sulfuric acid solution. That's the best way I have to turn calcium carbonate in the calcium sulfate of the choices I have available for you on the board. I agree. Why is that the best choice? Do you see that C versus D, I still have hydrogen sulfate ion as my sulfate source. So I still got to break H plus from sulfate ion. But that's not too difficult with hydrogen sulfate ion, because it's a weak acid, but its Ka value is pretty large, as far as weak acids are concerned. Okay? But here, beside hydrogen sulfate ion being my sulfate ion source, my acid attack is hydrogen sulfate ion. Here, what's my acid attack? Hydronium ion. And that's a hell of a lot better acid than hydronium ion. Than hydrogen sulfate ion, pardon me. So, if you pay attention to the acid-base chemistry we've talked about, you can recognize why. Of these choices, this is the way to go if you want to turn this stuff into that stuff. This also does it quite well. If you write the equilibrium reaction and calculate K, hydrogen sulfate ion plus calcium carbonate to make this stuff and this stuff, K value is huge. But if I use this stuff, the K value is even more huge. But if I use this stuff, I'm going to get a K value that's a good deal smaller than 1. I will not effectively convert calcium carbonate into this stuff if I treat the calcium carbonate with this stuff. Now, let's get to the last topic to be considered in Chapter 19, Section 19.4. First, a couple of general remarks about Section 19.4. In calculating the value for an equilibrium constant, for an equilibrium reaction which is composed of 2 or more fundamental equilibria, in Chapter 19, when we did this, we said at that time, what are the K's with which we are familiar? KW, KA, KB, and KSP. So in addition to these 4 K's, we're going to add one more equilibrium constant. And interestingly enough, of all the types of equilibrium constants that are known, we'll now have touched on every one of them. KW for water solution chemistry, KW, KA, acid ionization constant, KB, base ionization constant, KSP, solubility product constant, and now K sub F, formation constant for a complex ion. Now, I don't believe we've yet used the term complex ion. Perhaps we have. But we've already looked at quite a number of complex ions. If you look at the acid-base table, for example, there are two complex ions contained within. Hydrated iron +3 and hydrated aluminum +3. The term complex ion just about defines itself. It means an ion which is rather compositionally and perhaps structurally complex. Nothing fancy about this. I'm going to write a statement. So STMT is shorthand for statement. Complex ions are formed by Lewis acid, shorthand reference La, Lewis base, shorthand reference Lb. Reactions. Question. In Chemistry 2045, did you hear about Lewis acid, Lewis base reactions at all? If you didn't, that's okay. I'm just curious. Another statement. An an LA-LB reaction, Lewis acid, Lewis base reaction, is a reaction in which a coordinate covalent bond is formed. Back to Chemistry 2045. How many of you in Chemistry 2045 heard about forming coordinate covalent bonds? Nobody? Now I know you all talked about forming covalent bonds. The standard way by which the formation of a covalent bond is taught in 2045 is to imagine that reacting species A, like a hydrogen atom, comes together with reacting species B, like another hydrogen atom. And then the instructor will put a Lewis picture of hydrogen atoms on the board. H dot plus H dot. You've all seen this for a hydrogen atom, because a hydrogen atom has got a single valence electron. It's only got one electron. Its configuration is 1s1. Well, how is it that these atoms interact with each other and change their overall valence electron configurations when we make the hydrogen molecule? In the textbook, you'll probably see this picture. H dot plus H dot gets together and makes the two H's with a pair of dots between. That's the H2 molecule. What's the paradox? It's nothing but a representation for the shared electron pair which formed when these atoms got together, each of which had an unpaired electron in its valence structure. A covalent bond. Covalent because this thing belongs to each of the bonding partners. Well, when we form a coordinate covalent bond, we're making the same kind of bond interaction. We're going to wind up with a shared pair of electrons between the species that got connected together by the Lewis acid, Lewis base reaction. But the difference is, in making a coordinate covalent bond, One of the reacting partners supplies both the electrons to make the bond. And the other reacting partner supplies an empty valence orbital. Consider H plus the water molecule. There's a shorthand Lewis picture for the water molecule. These represent the two non-bonding pairs which you find in the valence environment of the central oxygen atom for the water molecule. H plus. Has H plus got any electrons? Has H plus got any electrons? None. So if this thing is going to bond with this thing to make this thing, with which we are quite familiar because of acid-base chemistry in Chapter 18, then it must be true. This had to supply both the electrons to make the bond. What did this supply? An empty valence orbital. What is the empty valence orbital that H plus has? 1s. Okay? Supplies empty 1s valence orb. Have you seen this before? Empty. It's empty, right? Empty valence orbital. Okay? And I do this to students because they tell me about energy and they write NRG. NRG. So I write back this. I mean, two can play at this game or more. Okay? Empty valence orbital. Whatever supplies an empty valence orbital, like the H plus in this reaction, is the La, the Lewis acid. And that which supplies the electron pair to make the bond is the Lewis base. Supplies electron pair to make the bond. That's the Lewis base. Let's write that down more clearly over here. La supplies empty valence orbital. Lb supplies electron valence electron pair. Usually a non-bonding pair. Which I abbreviate as NBP. All right? Now back to Chemistry 2045 and stuff which I know you heard about. How would you recognize a species to be capable of behaving as a Lewis base? How would you recognize a species to be capable of behaving as a Lewis acid? Let's talk about the Lewis base first. I give you the formula for a stuff. H2O, H3N, whatever. H2. How would you recognize a species to have the potential of behaving as a Lewis base? What would you do? Negative charge? Water doesn't have a negative charge. Just behaves as a Lewis base over there.
Draw the Lewis structure.
Yeah! You draw the Lewis structure and see if this damn Lewis structure has got one or more non-bonding pairs. Okay? I'll recognize. Draw. LS. I've asked you to draw LSs previously, haven't I? You think I might ask for some more Lewis structures on this exam too? Maybe exam 3, maybe the last exam, maybe forever? Did you learn in Chemistry 2045 that the most important property of any material, any species, any molecule is what?
Structure.
Structure! That's why this Lewis structure stuff is so important. You got to get a handle on structure for a material if you have any chance whatsoever to have an idea of how it behaves chemically or physically. All right? There's 4 species. I want Lewis pictures for these 4 species right now in your paper. I already gave you the one for H2. And after you write these Lewis pictures, I want you to tell me if this stuff can behave as a Lewis base. And after you tell me whether or not it can behave as a Lewis base, I want you to tell me, if you can, how effectively it will behave as a Lewis base. All right, let's put that one on pause for a moment. I give you the formula for different stuff. I want you to tell me if it can or cannot behave as a Lewis acid. What are you going to do to find out if something can behave as a Lewis acid? I've written 3 formulas here. Would you believe it's a fair statement that each and every cation, anything with a positive charge, can be a Lewis acid? Think that's a fair statement? Do you believe it's a fair statement that if something has got a positive charge, it's going to have an empty valence orbital someplace along the line? So, for this thing with the positive charge, if you want to know about its ability to behave as a Lewis acid and verify that, you should write its electron configuration, valence electron configuration, and see if the valence electron configuration shows the presence of one or more empty orbitals. So we'll write that down. Write valence electron config to look for empty. Watch out, there's empty again. Valence orbitals. So we're now programming you with the considerations that you have to make to find out if something can be a Lewis acid and find out if something can be a Lewis base. Before we talk more about the Lewis bases, we recognized about H plus as a Lewis acid because it's got an empty 1s orbital. And I told you, if something's got a positive charge, it's going to have an empty valence orbital. So any cation can be a Lewis acid. Doesn't have to be a cation. There are many species without positive charges that can be Lewis acids. But if you can write or recognize its valence electron configuration, you can decide. Specifically, Al plus 3. I want to know, how many empty valence orbitals does Al plus 3 have? Number of empty valence orbs. And we're going to ask the same question for silver ion. The silver ion is the ion whose complex ion forming ability will be investigated by us in just a moment. How many empty valence orbitals does aluminum ion have? Empty valence orbitals. I got to vote for 3. Any seconds? You did this in 2045. Now I want you to put it to use. How many empty valence orbitals does aluminum ion have? 3 is wrong. But at least it was a vote. 2. That's less correct than 3. 1. That's worse yet. 4. No. 6. No. Turn this into a random guessing game. 8. No. Well, we're getting close. Al. The Al atom's got how many valence electrons? 3. It's in family 3A, right? So what I'm going to make, when I make Al plus 3 from Al, all those 3 valence electrons are removed, are they not? Okay? Now tell me, Al, periodically speaking, where is Al found? It's found in period number 3, isn't it? I'm going to write something on the board and see if it rings a bell with you. Quantity 2n squared. Does that look like something you looked at in 2045? 2n quantity squared. Wait, no, I got this wrong. Let me write this correctly. 2n squared. Does that look like something you saw in 2045? You remember when you learn how to write electron configurations and you learned about this thing called the Aufbau order? Remember that? And you played this game. 1s2, 2s2, 2p6, and 3s2, and 3p6. What'd you write after 3p6? 4s2. And after 4s2, what'd you write? 3d10, you wrote that. Okay? Now 3d10. 3d10. Are we talking about energy level number 3 or energy level number 4? Third energy level, right? That 3, that's the principal quantum number n. Well, this recipe on the board tells you the total number of electrons you can put into an energy level. The total number of electrons you can put into an energy level. N identifies the energy level. How do energy levels correspond to the periods in the periodic table? H and HE. Period 1, N is equal to 1. LIBE on down through neon. That's period 2, that corresponds to energy level number 2. That means the valence electrons and valence orbitals for all the period 2 atoms are energy level number 2. Period 3, sodium, magnesium on down through argon. All the valence electrons and valence orbitals for period 3 species are energy level number 3. Okay? Now watch out. Here comes the tough game. N is equal to 3, right? We're talking about energy level number 3 because aluminum ion comes from aluminum and energy level number 3, period number 3. Here comes the hard part. N is equal to 3. What's 3 squared? What's 3 squared multiplied times 2? 18. Okay? That's the number of valence electrons you can put in there. And how many electrons can I put in an orbital? 2. So if I take 18, the total number of electrons I can put in energy level number 3, and divide by 2, what do I get? The number of orbitals. And for Al plus 3, since I stripped away all its valence electrons when I created Al plus 3 from Al, then it must have nothing but empty valence orbitals. Because it ain't got no more valence electrons. And only chemistry instructors and emperors of Byzantium can say ain't. Any emperors of Byzantium in here? I didn't think so. Although I did have somebody stand up a couple terms ago. Okay. So I want you now to name the empty valence orbitals that aluminum plus 3 has. All 9 of them. 3s, right? 3p. When I observe a p orbital, I find it to be part of a p sublevel. How many orbitals are there in a p sublevel? 3. So now I'm up to 4. But after the p sublevel is filled up in energy level number 3, what's the next kind of sublevel I run into? D dog. And a d sublevel is a package of how many orbitals? 5. 1 plus 3 plus 5 is 9. They're all there and they're all empty. Aluminum plus 3 has got 9 empty valence orbitals. So theoretically it can make 9 coordinate covalent bond formation interactions. It's never been observed to make more than 6. You realize that Al plus 3 is a pretty tiny thing? You got 10 electrons total being pulled by 13 protons. Al plus 3 is a pretty tiny thing. So it never makes more than 6 coordinate covalent bonds, because to do so, you'd have to get more than 6 groups, whatever they might be, like water molecules wrapped around aluminum ion. We already know that hydrate aluminum ion has the formula Al waters parent sub 6, not 7 or 8 or 9, because there isn't enough space, let alone there's not enough space to put these 9 water molecules around Al plus 3. Question. How many BBs can I glue to a basketball? A hell of a lot. Ha ha! But how many basketballs can I glue to a BB? 2. And the problem with Al plus 3 is it's too tiny to get more than 6 water molecules around it, or 6 anything else's around it, and have these things make contact. Because to make a bond, you got to make contact. So now we told you how to get Lewis acids. Now I want you to think about these things as potential Lewis bases. And that's what we'll start with tomorrow.